In this video, I'm going to go over the major things to know about the energy transfer model, which we abbreviated ETM. I'll go ahead and mention right off the bat that this is my go-to model. If I can solve a problem using energy transfer, this is the approach I'll use because very, very frequently, energy approaches are much more straightforward than approaches you could use with other models. And can get you the same information in a lot of cases. So the first big diagram that we used as part of the energy transfer model are the LOL diagrams, which included energy bar charts. The first thing to do, though, is the O part, which is that interaction diagram, where I'm making a note of the key objects. In this case, I'm going to do an example for a block that slides down a ramp. And I'm going ahead and marking those interactions. So there's going to be a force of gravity between the block and the earth. There's going to be a normal force between the block and the ramp. And then, just for the sake of this example, I'm going to go ahead and say this ramp is rough, and so there's a force of friction between the block and the ramp. It is crucial to define your system when you're dealing with energy. I'm going to go ahead and put everything in my system. So in this case, there are no external forces on my system, which means that my total energy is going to stay the same. So then I just have to think about what form of energy is present at each point in time, at each snapshot. So at the beginning of the problem, the block is going to have a whole bunch of UG. By the end, that UG will be gone. And as a reminder, I like to use blocks on my energy bar charts just to make it clear how these compare. So for example, even though my drawing's a little bit sloppy, I can tell really easily that I've got less kinetic energy at the end than I had gravitational potential at the start. And then because I've got a force of friction, that means I have some dissipated energy. So some of the energy in that system is going to get converted into heat, into sound, into things like that that tend to be very difficult to convert back to potential energy or kinetic energy. And so then I can write out a conservation of energy equation where the total energy I start with, so the UG, equals the total energy I end with, which is the K plus the E dis. Now, for the sake of this model summary, I want to go ahead and look at this same scenario, but with a different system. So again, I'm going to start with my interaction diagram. So I've got my block, I've got the earth, oh, and there should be a T in earth. And I've got my ramp. And I have those same interactions happening. I'm not changing the scenario at all. So I have the force of gravity. I have normal force. And I still have that force of friction. Now what I am going to do differently is how I define my system. This time, I want to put my block and the ramp in my system. So there we go. That means that the earth is now outside of my system, so I have an external force, which means that the earth is going to do some work on my block. So now for my bar charts, I'm going to approach it very similarly to how I did before, except because that force of gravity is now external to my system, that force crosses the system boundary. I can't store gravitational potential energy anymore. And so my block actually doesn't start with any energy with the way I defined this system. And so when I do my conservation of energy equation, instead of UG equals kinetic energy plus E dis, I'm going to have the work done by the Earth equals the kinetic energy plus the E dis. So make sure you're paying attention to what your system is when you're dealing with energy. All right, now that work has come up, there's another important diagram I want to make sure we touch on, and that is a force versus displacement graph. Now I've got the work equation from your formula sheet up here to just help reference. So if I have a force versus displacement graph, excuse me, if I have a constant force, then to get the area of this, I would do force times displacement, which if I look at this equation, force times displacement is equal to the work. So again, we have an example of where if you multiply two quantities together on the in a formula, then that means they are related to the area of that graph. So if I go to a scenario where I have a changing force, so instead of a constant force, I have one that increases as you stretch farther, like you might have with a spring. Then if I find the area of that, that's going to get me the work, which is also equal to the change in energy. And remember that you don't have to keep that in your head. It's all right to reason that out from the formula. So be able to reason out that if you multiply two quantities together, if you graph those and take the area of that graph, that's the same thing as multiplying them effectively. And then this last piece of the equation is for when the force is not applied in the same direction as the object's moving. So for example, if I have a box and I were to apply a force just straight to the side, I would use this middle part of the equation where the force has that little subscript that represents, or that uses the symbol for parallel. However, if I have a box that I am pulling upwards as well as forward, then essentially only part of that force does work, and so I'm going to use this last part of the equation instead. That doesn't tend to come up very often on the AP exam. And then the last thing is just a reminder of the major equations you have as part of this model. We have the equation for translational kinetic energy. So based on the speed of the center of mass. And while they don't do it on the formula sheet, a very, very common way to indicate that you're talking about translational kinetic energy, if both come up, is to do K with a subscript T. And then we also have the rotational kinetic energy. So this is when you have an object that is rolling or spinning or otherwise doing some kind of rotating. And this is often represented with a K and then a subscript R. And then we also have the equation for spring potential energy, which is related to K, which tells us about the stiffness of the spring, and X, which is how far the spring is stretched or compressed. And then we have gravitational potential energy, which is related to mass. It's related to strength of the gravitational field, which is that 10 newtons per kilogram. And then delta Y is just how far above whatever reference point you pick. And so you can always choose where gravitational potential energy is 0 to try to make the problem a little bit easier.